Hello, hello, hello. Good afternoon, Internet. Welcome. Welcome to yet another NL Math Man Math Help stream. Here, we're going to do an NL Math Man Physics Help stream a bit today, actually. It's not just going to be math. Oh, hold on a second. Hold on a second. I just noticed something. I gotta fix something in meat space. Hold on. Let me disable my video for a second. Boop. Wee, whoop. Disembodied voice now. Aha, look, I'm emanating from around this classroom. Ooh, I'm a ghost. I'm a ghost, a scary ghost. Okay, now we're back. Now let's see. Now, yes, there we go. Now I can lean back and my chroma key doesn't have a conniption fit. Good. Okay. So we're here now, day 38. Day 38. This is the end of week 8. It should have been day 40, you'd imagine, but there were two holidays in in sort of the list of weeks that we've had. We also had a full week off, like I keep reminding people, and a week at the start. So really, this is week 10. This is the end of the 10th week of distance teaching, as far as as far as I'm concerned, as far as the amount of work I've done is concerned, right? Because that first week of you know impromptu setting up like a DIY distance teaching system with it's sort of a bespoke distance teaching system entirely based on just ideas that I had in my head. Um, that was an effortful week as well. So we've been here holding the fort down for 10 weeks now going on. And we've got another we got another six, I think 5 weeks. Yeah, one more week in May, right, and then the 4 weeks in June, and then then it reaches the end of AESL's funding for the satellite ABE campuses. So after that point, I assume that'll be the end of her. I gather. But we'll see how that goes when the time comes. Here now, my background for today. We're seeing. I was looking down through some old pictures and stuff to see what I was going to talk about because you notice over this week now I've been humoring myself in talking about stuff that I've done in the past as opposed to just nice pictures of cute doggies, which I will return to at some point in the future, of course. But for today, I thought I would be a little bit more. I don't know, common. I don't know. Maybe that's the wrong word. I just wanted to show, my home for a year. This is what we see here now. This is the classroom that I taught in when I was teaching in the UK. Right. This was one of my positions. This is the 1 year one I had in Surrey. Right. And we can just see a little bit of the I don't know the details of what I used in my teaching practice there. See up below where it says stream start soon, you'll notice there's a nice um, sort of number line that I hung from a string going across the classroom. It was hung out from the wall, and the reason you hang that out from the wall as opposed to putting it directly on the wall is you want students to be able to come up and stand it under it, and then be able to move around and stuff like that, right? This picture is from one of the last days of classes, so my desks are arranged a little differently than I had before. I didn't have it in like this sort of Wi-Fi symbol, sort of concentric arcs throughout the whole time I was there, right? But this was, I believe I took this picture like right at the end, right? You can see there by there's a door out to one of my colleagues' rooms there in the sort of the top right of the room. To the left of that, you'll see that stack of books. You see all those? All those like those are all big like clear folders, right? That are all jammed full with all the student work from all the different classes that I had. Because I had 5 different math classes and one elective class, and then yeah, all the books would have been kept in the room in there. Um, yeah, I kind of wanted to go over to return to talk a little bit about my math game that I played in this class. This is where it was invented. You can just barely make out the box that it was in on the one of the middle shelves there behind my desk, right? Mathemagic, that math game that I did out of Magic the Gathering cards that I talked about um, on that weird little aside stream that I did about um, about educational games, which maybe I'd return to at some point. But um, I've been I've been more than a little swamped, so not really ready to prepare much talking about educational games these days. Um, I did want to introduce a new sidekick. Actually, it's a big deal for my stream today. I'm actually going to introduce my new sort of support character, right? And it came from this classroom. It was something that oh, hey Slayer Darth, good morning, or afternoon or evening for you, I guess. 4:30, right? Yeah. Um, yeah, I don't mean a new TA or anything like that. I mean my new on-stream visual sidekick that I found out of pictures that I saved. 4:36 p.m. Yes, right, 3.5. This is GMT, offset by 6 minutes. Yeah. So here we go. We're gonna see. This was drawn by one of the students in my class when I was up there, and we're gonna call. Here we go. We got NL Doodleman, right? That's this guy. NL. This was supposed to be me. I've cropped out my last name to. Can I be your off-screen PA? Yeah, you can be my TA, my teaching assistant for sure. This guy is NL Doodleman over here. This will be my mascot, maybe. Right? I dig. I mean, I don't know why they included a cigarette in this. Like, I don't smoke. I don't smoke cigarettes. And the students have never seen me smoke. But I do kind of dig how it gave off like a Cowboy Bebop vibe. I thought that was pretty great, right? So here it is, this NL Doodleman. Maybe I'll crop the picture and maybe I'll just do my own one instead of taking the one that a student drew in like 30 seconds. I just was looking through pictures and I thought it was funny. Johnny Carcinogen. There we go. Yeah, that's good. Yeah, it's like Johnny Carson, but Johnny Carcinogen. Yeah, there we go. I like it. That's good. It's a good. Anyway, I'll just trail off that sentence and then carry on. Whatever. Right? No one's really paying attention to what he's saying. Um, I'm gonna move on now after just sort of showing this picture that matters mostly just to me. Um, let's carry on with some math for today. I actually have some quite different stuff to talk about today, right? I'm going to be doing some discussion of the physics courses, right? I'm going to talk about significant figures, intro to distance time graphs, and then rearranging some common physics formulae, right? But it's basically the same as math because all those things are used in math. Really, we don't use sig figs as much in math courses, but they do come up, right? And then rearranging the common formulae. Well, that's just algebra skills, right? And I don't mean to belittle it when I say it's just algebra skills. It's still relevant things that we need to know, but it's not really specific to the exact physics. It's more just knowing how to rearrange the algebra, right? Then I'm going to do some cross multiplying with sine law and some sine and cosine laws and angle properties. Um, yeah, so Betty Ann, that will be for. I am partly done the correcting of the work that you gave me this morning, but I am, boy oh boy. Let me send you a sig fig screenshot. Okay, great. Yeah, that sounds good. Yeah, I have been. Oh boy, just run off my feet here this morning, just massively with new fires popping up to go put out and all this kind of stuff. So yeah, I'm going to just get stuff done as it gets done, right? You know. But first up today, like I said, I'm going to talk a little bit about the physics stuff, and I wanted to start off with page 358. There's some stuff on 358 of the physics textbook. So Troy, this is the physics book that you're on to these days. It's this guy over here. So I'm going to zoom in a little bit here. I did. Let's see. Well, first I will just before I get into the actual questions, actually, before I get into those, how about I just explain a little bit about the significant figures? Okay, yeah, Slayer Darth. Yeah, that's a good shot there. I see what's going on there with those sig figs. Yeah. Okay. But I'm going to go over here today now. Is first up, let's just ignore that part up in the corner there because I'm just for this first bit, I'm just going to talk a little bit about what sig figs are for our purposes, right? So this is going to be physics 1104, and this is going to be unit 1. Although it doesn't really matter what unit it is and all that kind of stuff, right? But significant figures, or rather, so significant figures basically they show the degree of precision of our measurements, right? And Troy, when you did the definition for that, you said that it's one beyond sort of the well, there's like if there is one beyond the number of digits that we're 100% sure of, right? So just to show what that kind of means, say if we had a ruler like this, right, that's gradiated in millimeters versus one that's gradiated in centimeters. Say we had a line that was exactly, I don't know, I'll draw it even on a side with no measurements. So say we had this line here that's this long, right? It's that line there. If I was to measure it with the centimeters side, I would see here that it goes, well, it goes past 1, 2, 3, 4, 5, and it goes past 5.5, because this one has a half marker. But let's assume it didn't have a half marker, right? But we know that it's past 5, and we can guess that it's about 5 point, I don't know, I can guess that it's about maybe 5.7, right? So I can say that this now has two significant figures because I've measured it with this side. Because we're absolutely sure of the 5, because we see that it's past the marker here for 5. But this 7, I'm not 100% sure about, right? So that's just an approximation that I use based on a bit about how far past the 5 it goes. It's 2SF or 2 sig figs, right? Because we always go sort of one past the finest gradation of our measuring tool, right? So to say I was to measure it now with this side over here instead, right? Because this side over here now has millimeters. So now I see that it's actually 55, 56, 57, 58. It's actually 58, and it looks like it's exactly 58. As far as I can see, it looks to be exactly 58 millimeters. And since it's exactly, I'm going to say 0.0, right? Because from here now, these two digits I'm sure of, and this one I'm unsure of. So this now has three significant figures, right? Because we take two values, we take whatever values that we're sure of based on our measurement, and then one past that. And that's what we consider to be our sig figs, right? So here we've got three. Significant figures or significant digits is exactly the same thing, by the way. So most of the time I'll call it sig figs because that's just what I'm used to calling it. But you will see it called significant digits sometimes as well. Those are completely interchangeable. Okay. Um, so there are a few sort of small rules about sig figs that we need to get to, right? So they show the precision of measurements. I'm going to say counted. Hold on just 1 second. In Twitch chat, I think I got a. Nope, nope, that wasn't important. That wasn't important at all. Okay, never mind. Didn't have an important message. So counted or non-measured or discrete values have effectively infinite sig figs. Right now, I mentioned that on the notes, Troy, that I sent you earlier. But there, say for example, here we measured that this was 58 meters, right? 58. Sorry, not meters, millimeters. My goodness, my goodness. Okay, right? But I measured that it was 58 millimeters. Say we had two lines that were both 58 millimeters, that I measured both of them to be 58.0. Say we had another one that was exactly like this, right? So two lines at 58.0 millimeters. What's that? 166. What am I doing? 116 millimeters. Right? There we go. So two lines measured at 58.0 millimeters. If we had two that were exactly like this, would have a length of 2 times 58.0 equals 116 millimeters. So still three sig figs, right? Because we don't say, hey, there's two of them. So because the number 2 has one sig fig, then we need to have one significant figure in our answer. That's not how this works, right? Because we've counted the number of lines to be exactly 2. So this 2 here, even though it looks like it's got one sig fig, you can actually treat it as 2.000000000, right? You could add as many sig figs on there as you wanted to, as long as they were all zeros, and it would still work. Because this is a counted value, not a measured value. Or in other language, we call this is a discrete value, whereas this is a continuous value. So discrete values don't have sig figs, right? Because they're counted and not measured. There's some other sort of strange rules about sig figs. It's that so leading zeros are not sig figs, right? So if we have, say, the number 0.0013 has two sig figs, right? Because all these leading zeros here, they don't matter. Because really, what it boils down to is significant figures are numbers that you would have to write in if you were writing the number in scientific notation, right? So I'll put that there in an aside in a different color, kind of like sort of another rule that we're doing is actually, hold on. You know what? You know what? Hold on. I'm talking in circles here. Give me a second, and then we'll get back to what I was going to talk about. But really, it's scientific notation is what it boils down to. Now, I don't believe you've been introduced into scientific notation quite yet. It's a little bit backwards, in my opinion, to do sig figs before scientific notation. But either way, I'll get to that in a second. Um, Zeros between non-zero numbers are significant. So say like the number 1002, that has four sig figs, right? Because zeros that are between non-zero numbers are significant, right? So that one's, all these four are significant because 1 and 2 are non-zero, right? Zeros following numbers without decimals are not significant, right? So for example, the number, say, 32,000 has two sig figs, right? So 32,000 doesn't have, well, we'll see in a second, but 32,000, if we wrote it in scientific notation, only requires two characters, right? Or two digits, really, more characters, because anyway. But it's the number of digits that are required if we're writing it in scientific notation, basically. Zeros following numbers with decimals are significant. Okay, so say I had, like, I don't know, 2.750, that actually has 4 sig figs, right? Or if I had 32,000.0, right? This one now actually has 6 sig figs, right? And why is that? Why is that? Well, just to explain it a little bit, it goes back to the same thing I was saying up here, is that significant figures exist in order to show the smallest gradation of the tool that you've used to measure this quantity, right? So say someone said, oh, it's that wall is, or that road is 32,000 feet long, right? 32,000 feet. If someone said like a road was 32,000 feet long, it sounds like it was estimated, right? It sounds like maybe you just measured it to the closest thousand, right? And if it was rounded and measured to the closest thousand, then only these 2 digits here would be significant. But if you say we measured this road and we found this road to be exactly 32,000.0 feet, that would imply that you actually got, you know, a a measuring wheel or whatever, and you measured it, and it was exactly 32,000, even to the nearest tenth of a foot, right? So here now because of this point zero, you're telling the person who looks at this number, hey, we found it to be exactly 32,000. It's not rounded. It's not approximated at all. So this has 6 significant figures. But this one up here, if someone saw that, they would say, oh, well, that one is rounded to 2. Now, unfortunately, we don't have an easy way in the number like this of displaying this number as having 3 or 4 significant figures, or 5. We would have to go right to the 6 in the way it's written out here. But in the scientific notation, you can, right? So really what it boils down to is significant figures are the digits you have the right to display a number in scientific notation. All right? So scientific notation. Oh, is my cam shaking today? Oh, it is a bit. Why is that? Why is that camera shaking? I've got it put on a separate table. This table shaking shouldn't be messing with my camera. Anyway, so significant figures are the digits you have the right to display a number in scientific notation. Right? What is scientific notation? Well, scientific notation, say for 32,000, right, to go back to that same number, that would equal 3.2 times 10 to the 1, 2, 3, 4. Right? So that has 2 sig figs there because it's a 3.2, then it's times 10 to the 4. Right? And this is why zeros afterwards and zeros before don't actually enter into scientific notation, right? Because then if I was to do, say, 0.0013 like I did above, that's 1.3 times 10 to the negative 123 times 10 to the negative 3, right? And if you're, I can't recall if you covered the scientific notation part in any of the other courses that you've done so far, Troy, but as a real quick sort of breakdown as to what it is, this times 10 to the power of something, this just means, how far do we have to move the decimal to get from this notation back to the actual number that we're dealing with, right? And for these numbers, which are relatively small for scientific notation, it's not super useful, right? Because 32,000 versus 3.2 times 10 to the 4, well, that's almost as much work as writing out this one, right? They're pretty similar, right? But to say instead I went with one of my favorite math examples in the world. Here's one of my favorite. This is statistics now for a second, just a hot second, just bear with me. But if you take a regular deck of playing cards, like a regular, hold on, hold the phone. You take like a regular deck of playing cards, like these touristy ones that I bought before I left London, right? Okay. So if you were to take a regular deck of playing cards, right, just 52 cards like here, like this, It's only 52 cards, right? Just a normal deck like everybody's seen a whole bunch of times. How many ways can I rearrange this deck of cards? Just these 52. Well, it's 52. There's 52 options for the first card, right? There's 52 possibilities there. Then I've got one taken care of, so now there's 51 left, right? So there's 51 possibilities for the second card, 50 possibilities for the third card, 49, 48, 47, and so on, right? So how can we represent how many different possible orders of these cards that there are? Well, there's a function that we have for that in the stats. It's factorial, right? In factorial, in your calculator, well, if you're using one of these guys, it's over here. But this, it's an exclamation mark, and it means 52 multiplied by every number smaller than it, every integer smaller than it, down to 1. We don't multiply it by 0, of course, because then the whole answer would be 0. But once I click enter here, you're going to find out how many different possible orders of this simple looking deck of playing cards there are. Let me click enter. What the heckarino is that? All right, that is, see this E? E is just a small capital E is another way of writing times 10 to the power of. It's just people took scientific notation and made it even shorter, right? But say, instead, if we had 52 factorial, that equals 8.0, I'll call this 8.06 times 10 to the 67. Times 10 to the 67. That means if I wrote out just how many different ways there are to organize this deck of playing cards that I have in my hand, simple looking deck of cards, it's actually 8 with 67 zeros following it. Like it would take me 5 minutes just to write out this number, right? And 8 with 67 zeros. You know, that's actually like theorized to be what, like more than the number of particles in the known universe? Like that's a crazy, gigantic, ridiculous big number. And it's amazing to me. It's totally mind-blowing that something as simple as a deck of playing cards, something that everybody basically has seen, everybody's shuffled a deck like this before. There's so many different orders of this deck of playing cards that it's statistically likely that if you take a deck of playing cards and shuffle it, like I'm about to do, if you shuffle a deck, which I've clearly done once or twice before, if you shuffle a deck of playing cards, it is statistically likely that this is the first time in the history of the world that this specific order of cards has ever existed. That's amazing to me. That no matter how, you know, even with like people in Las Vegas shuffling cards, like individual dealers shuffle hundreds of hands a day, thousands maybe, right? And it's still, even with all that, it's still statistically likely that every time you shuffle a deck of playing cards, it's the first time that exact order of cards has ever existed in the history of the world. Like, right? Like crazy. It's such a ridiculously big number. But that's why we use scientific notation, is because of numbers that ridiculously big, right? Because I'm not, like I said, I'm not going to sit here and write out an 8 with 67 zeros following it. That would just take me most of the day. But I can just do times 10 to the 67 and then we're there, right? Kind of like you'll in your course as well. I believe you get into the speed of light, right? The speed of light is actually in a vacuum is actually 3.00 times 10 to the 8 meters per second, right? And that is the lowercase c, which is, you know, our friend in chat, the real Albert Einstein, should be able to tell us how that number is derived, right? But that is, you know, that's another example, very common example of scientific notation. We don't tend to write out the 3 with the 8 zeros following it. It's actually more like 2.99, some people will say, 2.99 times 10 to the 8, but whatever. Well, I like a nice round 3.0. It looks good. But either way, you know, I take any excuse I can to do the whole, like, you know, showing off how much complexity there is in a deck of cards, right? But, like, just like it isn't the fact that like life evolved in the first place like so ridiculously amazing when you consider that something as simple as a deck of playing cards has so much complexity that, you know, we're still finding new orders of playing cards that have never existed, right? And you combine that level of complexity with like a biological system that, like, you know, creates that has amino acids arising spontaneously out of the primordial soup and stuff. Boy, oh boy, oh boy. Like the amount of complexity that exists in natural systems is just mind blowing. Anyway, anyway, this is not a stats lesson right now. Although maybe I should do NL Stats Man. Maybe that'll be my next digression. But okay, so to get back to the topic at hand, scientific notation is, a way that we write really big numbers with fewer characters, right? But if I was to take this 3.00 times 10 to the 8, the way it's written here, right? This is 3 sig figs, right? And this 8.06 times 10 to the 67, this is 3 sig figs, right? But as you see here, I do 3.00, right? Why do I do 3.00 and not 3? Well, that's to show that this number has 3 significant figures, right? And like I said, it always goes back to how it's written in scientific notation. And like I said up here, right, from this number, this has 2 sig figs. This number now has 6 sig figs, and we don't have a way of representing this exact number in normal notation with the number with 3 sig figs or 4 sig figs. But in scientific notation, we can, right? Because if we had, say, 32 point, 3.20, because our decimal, in scientific notation, your decimal should always come after the first non-zero digit. But if we had 3.20 times 10 to the 4, this one is 3 sig figs. Or 3.200 times 10 to the 4 is 4 sig figs. And I mean, you see where I'm going with this. It's 5 sig figs. But the number is still the same, right? Like if we were to calculate it out and say, what number does this represent? Well, this still represents 32,000. This still represents 32,000. And this still represents 32,000. But it's different. It's ways of showing it with a different number of significant figures. Boy, that was a bit of a rant. But that hopefully is a decent intro to what you'll be using significant figures for and what they can measure, right? And it does all boil down to scientific notation, which is basically just a small way to write really, really friggin' big numbers like this. So now I wanted to talk a little bit about a few of the questions, Troy, that you had done. Now you were doing these ones really well, so these aren't like issues with how it was completed or anything like that. I do just want to go down through some of these, especially this first proof here, number 5. See number 5 up here on the side? Show that 1 meter per second equals 3.6 kilometers an hour. You got this one right for sure in your notes, but where you were typing your notes instead of handwriting it, or instead of using like I'm not going to require you to go and get like there are math extensions that you can get for Microsoft Word and stuff like that, where you can actually type math characters into Word, or you can do it in like Wolfram Alpha, or you can do it in Desmos or various other sort of calculators. Just for the sake of keeping these courses relatively simple, I'm not going to require you to go online and like teach yourself any of those things. If you're interested in doing it, I can't help you with those. But for purposes of these ones, I think drawing it out by hand is perfectly fine. If you want to send me one file like you did, which was quite useful and was well edited, so it's a good job with the computer there, you can just take a picture of it and crop the JPEG and stick it into a Word document or something, right? So let's keep it simple, basically, right? No requirements to go download Mathematica or something like that, right? Although Mathematica is incredible. As physicists will tell you, right? Instead of writing out every step of a proof, you can just say, "'Cause Mathematica said so." But if you're a mathematician, you got to write out every bit of that proof. You can't just say, "'Cause Mathematica said so." Like, what sort of a pleb would trust a calculator? You got to show all the workings if you're a mathematician. Anyway. Physics 1104, and this is Unit 1 still. This is page 358. Okay, and question 5. So show that 1 meter per second equals 3.6 kilometers an hour. So how's about, I'll show it this way. So a meter per second is 1 meter per 1 second, right? Like, that's not hard. But what does a meter equal in kilometers? Well, 1 meter, and this is, Troy, this is very much the way that you solved it, but I want to show you sort of like the one last step of synthesizing it all together. The 1 meter is, of course, 0.001 kilometers, right? And 1 second is one out of, well, there's 60, it's 1 out of 60 for minutes, and then there's also 60 minutes in an hour. So it's going to be 1 out of 3,600, right? It's 1 out of 3,600 hours. So if I put this one into meters, I get that. This one into hours, I get that. And I'm actually going to leave it as a fraction here, and I'm going to put a fraction in the denominator, and we're going to see what happens, right? So we've got 1 meter, which is actually 0.001 kilometers. That's going to be divided by 1/3,600 hours. Now, of course, from the sort of the algebra like this, if we're dividing by a fraction, remember, we saw this in some of the earlier courses, the intro courses. If you're dividing by a fraction, that's the same as multiplying by the fraction's reciprocal, right? So it's actually going to be 0.001 km multiplied by 3,600 over 1, right? Well, I'm going to, yeah, anyway. So what we're going to get is, yeah, I mean, this should actually be 0.001 kilometers per meter divided by, anyway, I'll save you putting in the units there now. 0.001 times 3,600, which is, of course, going to get us our 3.6. Right? So, this is just sort of the way that I would want to see it written out. Something like this. It doesn't need to be exactly this, but if it was on a test or something like that, I would want to see the algebra working written out a little bit like so. Okay. Let's see. I mentioned question 6 to cover as well. Use the conversion factor in question 5 to convert those ones. Yeah. You did these ones correctly mostly. I just wanted to bring up, there are significant figures a little bit here. So for 6A, and yeah, there's a teachable moment here that's actually not covered in these questions. So I'm going to go over this. So we've got 92 kilometers per hour, and we want to turn that into meters per second. So we're just going to divide by 3.6, right? Because a meter per second is considerably faster than a kilometer per hour. So 92 divided by 3.6 is going to give us 25. Now, am I going to call this 25.6? What am I going to call this? I'm going to have to call that 26. Because I need 2 sig figs in my answer, right? Imagine instead that we had a question where it was, say we were doing 103.8 kilometers per hour, and we wanted to convert that one into meters per second. Just imagine we had that question. Then what are we going to do? Well, it's still going to be divided by 3.6, right? But then what's it going to equal? Well, it's 103.8 divided by 3.6. It's going to get us 28.83. Do we call that? So what do we call it? Do we call it 29 or do we call it 28.83? Well, we call it 28.83. Why? Why would we use 4 here? Because this number here has 2 sig figs, doesn't it? Right, but this number here is exact. That's the thing, right? The 3.6 is not a measured quantity. We know that there are exactly 3.6 kilometers per hour for every 1 meter per second. So since this is an exact sort of conversion factor or an exact quantity that's not measured, we don't need to have that be part of our sig fig calculation, right? So this is another reason why, to be honest, I kind of prefer the way physics teaches math. to the way that math teaches math in a lot of cases, because the physics makes it very clear that you need to be constantly thinking about what the numbers in your algebra represent, right? And I think that's something that's missing a lot of the time from not necessarily the way teachers teach the math, but from the way that because oftentimes when students are learning math, they try to just see the quickest way to getting it to getting the answer that's given to them, and so it's sort of like a rote thing where it's kind of like, oh well, when these numbers are in this position, I just do this, and you don't really learn why, right? Whereas in physics forces you more to learn the why because it's applied math, right? So you have to be able to understand here this quantity up top. This was a measured quantity. Therefore, this has significant figures, and it has four significant figures. This one down here is not a measured quantity because it's your conversion factor, so that's not considered as part of your significant figures calculation. Okay. I did also want to do question 7 over here because I mentioned at the start. Oh, sorry, that wasn't question 7 there. It was. Oh, hold on. Hold the phone. Hold the phone. Let me just go back over to my intro screen for a second. Stream starts soon. No, it's already going. I want to do the rearranging common formula one, common formulae, because we did. Oh, did I not copy down the page for that one? Oh, sugar. Oh, crappy. Okay. Okay. I didn't actually copy down the page number for that one, it turns out. Well, um, just hold on one quick second, and I will bring that up. I won't be able to bring it up to show, unfortunately, but I can bring it up just to see for my own purposes, so I can then see what exactly it is that I've been sending people. Oh, that was page 349. Oh, crud. I didn't, I got to scan all these things into my computer, and I didn't actually scan in page 349. Okay. Um, but I am still going to do a few of these rearranging formulae. Okay, so let me just skip back on over then to my working display. Here we go. So we're going to do rearranging formulae here. There we go. That's a picture from your textbook. Let's just have that hang out in the corner there, all nice and fancy. So the rearranging formulae, there were a few questions like this one, like say question, I believe this was 7C on page 349. 349, question 7. So 7C, I wanted to go over this one. So for this one here, we have just the normal straight line graph formula, right? Y equals mx plus b. And the question asked us to rearrange that one to get x by itself. And this is a good sort of cross-curricular lesson because the math units do this as well as the physics ones, right? So here now, well, to rearrange to get x by itself, we just got to get rid of the other parts that are around it, right? And in general, when we're rearranging stuff like this, we sort of do the opposite of bed mass, right? Because oftentimes, hold on a second. So we're going to do the opposite of bed mass. So normally, in bed mass, we would do multiplication before addition and subtraction. But here I'm going to get rid of the addition and subtraction before I get rid of the multiplication because I want to sort of move the parts away, right? So I'm going to have y minus b equals mx because I've now moved the b over to the other side. Now I'm going to try to get this m out of here, so I'm going to divide by the m. Y minus b over m equals x, like so. Right? That's just a little bit of, that's just the way we would solve that one. Let me see, which other ones were there? So for the next one, we have, right, so this is a equals half base times height, right? So that was the next one that you had to do, which is just the formula for the area of a triangle, and you were asked to rearrange to get b by itself, right? And Troy, I believe what you did was you called this a over a half h equals b, which is fine. It's fine to call it that but generally we don't leave it like this. We can do this sort of part way through, but that's not normally how we would leave it in the end. Uh, Actually, the meter is a number of wavelengths light in a vacuum when burning a krypton isotope. Okay, cool. Yeah, I like the sound of that. That's a good. So that's a technical definition of a meter. I like it. Number of wavelengths of light in a vacuum when burning a krypton isotope. That's pretty cool. So it's like the wavelength is partly determined by Superman, is what you're telling me, right? So the meter, yes, the meter is determined by Clark Kent, right? That was the moral of that story? I hope so. I'm aware that Krypton is real, whereas Kryptonite is perhaps less real, but you know, it's important, obviously. But we wouldn't leave it like this in the end normally, because dividing by a half, like I mentioned up here, dividing by a fraction is the same as multiplying it by its reciprocal. By its reciprocal. So if we're dividing by a half, it's the same as multiplying by 2. So we would call this 2a over h equals b. Right? Batman is real? Yes. Batman's a scientist. We all know that. And scientists are real. Therefore, Batman is real. Right? Like that, doesn't that logic work? That makes perfect sense, doesn't it? Like, scientists are real. Batman is a scientist. Therefore, Batman is real. Right? That's totally ironclad. There's no problems with that line of reasoning. A second is measured from cesium. Okay, so it's the radioactive decay of cesium. Yeah, I like that. Um, yeah, instead of like being just the average length of a day split into however much, right? Because we know from atomic clocks that the days are not actually always static, right? That's why we have that leap second, right? We actually had to pick up a little bit of time occasionally in order to make up for the fact that you know the rotation of the Earth has changed slightly. So yeah, for the radioactive decay of cesium measures a second. That's pretty cool. And then for question E, no, you had I think question E wasn't a problem. Question F, then right. So the question F, what you had is area equals pi r squared, right? So to rearrange this guy is going to require a square root sign, which is a real pain in the ass to try to type out on a computer. I know that, right? Like just typing out in a normal word processor is really going to be a pain. But this is the answer that you're looking for, like so, right? With the square root sign over the lot of it. If you're trying to write this one out on in like Microsoft Word or something like that, what you could write this as is r equals a over pi. We usually use this symbol instead of the dividing sign, but that's fine. And you would put to the 0.5, right? And you can either use the hat symbol like this, which is what shift 6, I believe, on your keyboard, or you could call it r equals a over pi to the 0.5 with a superscript font, right? So Troy, you could use either of those if you wanted to be typing those ones out. Again, right, typing out math can be really time consuming. So I would encourage you to just to do it up by hand, right? And then you can take pictures and then like just cut and paste it into your Word doc or whatever your PDF. Um, yeah, I mean, I don't know exactly what editor you use to make that. It looks like it was done in Microsoft Word, which I would recommend. Like Word's a pretty robust program actually. It's fairly simple, but it's pretty good, right? Wondered why I found quadratic expressions so difficult once upon a time. Hey, quadratic expressions are great. I love that quadratic expressions have this out that you can use. Like if you're ever confused about them and like I can't see how to factor this one, just break out the old standard, man. The negative b plus or minus the square root of 4a 2b minus 4a cl over 2a all over 2a. Anyway, that's right, isn't it? Yeah. Anyway, got that on the corner of Troy's physics work there now. But yeah, the quadratic formula does allow you to. Because it took this past year to learn everything from scratch, going through the rudimentary maths. Yeah, yeah. It's hey, from the ground up, like each level of math builds on the previous level, right? So it is a really good idea if you've got any gaps in your knowledge, or if you're trying to just learn it for your own sake, right? To expand your knowledge. Starting at the basics is a really good idea, even if it seems fairly intuitive, like oh, I'm so bored with this early math. It's still worth starting there. Let's see. Did I want to mention this one here? I think I'll skip over here now, and because the next topic that I wanted to talk about today was, oh yes, intro to distance time graphs. I wanted to do a little bit on that. Troy, I think your understanding of distance time graphs was pretty good from what I saw. I did want to talk about it a little bit, right? And I'm going to do this one here, car crossing Confederation Bridge. So it tells us to plot a distance time graph using the information in table 4 and draw a best fit line. Well, you did one better than me. You did it on computer. I'm just going to do it by hand here because I just want to do it quickly. I was going to show you how to do a graph like that in Excel, which I will do at another point for sure. Maybe Monday I'll show you how to do those. The problem with doing it in Excel is that when it tells you to plot them like this, we do kind of want you to do it by hand, right? Because the calculator is, I mean, it's not cheating, but it's close, right? But you can use something like Excel to draw a distance time graph like this super easily. So I'm going to mark off lines every centimeter. Like drawing like bar charts and pie charts by hand rather than using Excel is just like, why are you, what are you doing? Why are you, but sometimes these courses tell you to do it by hand, so we make do with what we got. Okay, so let's see. After 2 minutes, it's at 2.4 kilometers. So I'm going to call this 2, 4, 6, 8, 10, 12, 14, and so on, right? And I'm going to call these distances the same, 2, 4, 6, 8, 10, 12. And of course, I had to label my axes because I'm trying to model good behavior here. This is time in minutes, and this over here is distance in km, like so, right? So now mine is not on grid paper because I still haven't gotten any grid paper in. Um, oh, that's what I should make sure to order. I'm gonna try making some orders from Walmart sometime soon because they do like pickup and all that kind of stuff. So I'll see if I can't get some graph paper from Walmart as well. So this first one is 2.4. At 4, it should be 4.8. So I'm just eyeballing these ones in the middle, of course, which is why my graph is going to be a touch off. 6 is going to be 7.2, so just a bit over halfway here, like so. And are these lining up relatively straight? Not bad. Not bad. I'm just going to go ahead and draw the line here. I know this is not the way we were supposed to do it for this question, but I'm just going to go ahead and sort of draw the line there like that, right? Just to get it a little bit quicker. Okay, so plot a distance time graph and do that. Okay, using your graph, find the distance traveled after 5. Okay, so 5 is here in the middle. So you go up there to 5, and we see 5 is, yeah, 5 is about 6. So this is part A for that question. Or this is still physics. 1104 unit 1. It's a good one there. Using your graph, find the time required to cross the bridge. So the bridge is, what was that? You see at the top here, because this is talking about Confederation Bridge, and it's 12.9 kilometers long. So 12.9 is going to be about here, nearly halfway between. So that is looks like it's going to cross around there and go over to about, oh, I'm gone off my chart, like 14-ish. Um, oh, never mind, never mind. No, no, what am I doing? What am I doing? I've got to show this correctly, not. What am I doing? Now it's 12.9 kilometers, right? So the distance is in kilometers over here. So 12.9 kilometers. Let me keep drawing these ones out because I'm going to need a bit more. 12.9 kilometers will be almost halfway up here, right? Because I got to measure from this side and then come over here and then go down. And I'm going to find it's a little bit over 10 minutes. So I'm going to say maybe about 10.2 minutes. Okay, there we go. So that's about that one. And then D was the speed constant. Explain how do you know? So this is what I wanted to get onto talking about here, right? We can see the speed is constant. You can see the speed is constant because the graph is a perfectly straight line. Now, of course, this is the kind of stuff that can only really exist in a textbook, right? The even the notion of perfectly constant speed, right? But that is the way that we would find, um, excuse me. So that is how we would show that it's constant because it has a constant slope. And that brings me to something else that I wanted to mention as a bit of an aside, but it's another example of how even math that's a lot more advanced than even what we're going to be doing in this entire program really can be used here, right? Because if we were to graph this as a line, what's it going to be? Well, our slope, we know that our slope is 2.4 over 2, right? Or our slope is 1.2, right? And then there's a thing called the derivative, right? The derivative is something that we see later on in calculus, but the derivative of a line is the slope of the line, right? So if we were to take the so this is a total aside here, right? Because this is something that you're not really going to see um, unless you go on and do more math afterwards. I mean, I know that that looked fairly easy, but the derivative is sort of a way that we like any constant term just ceases to exist. A term with a variable of one, we sort of take the number in the corner and we move that down here in front, and then we decrease this one by one. So it actually becomes 1 times 1.6 times x to the 0, and anything to the 0 is 1, and then 1 times 1.2 stays as 1. So we actually end up with the derivative here is 1.2, which is the slope of the line. And it's constant because we can see it the whole time. But anyway, this is just it shows that even this sort of fairly rudimentary sort of introduction to physics here with this distance time graph can still benefit from math that will learn a lot later on, and it starts showing how even something that at first seems like why are we learning this calculus nonsense, but it actually has geometric applications. It has applications back with say distance time graphs, and if I took the integral of it, the integral would find me the area underneath the graph, which would be the distance that has been traveled in total thus far, right? But we'll, I'll spare you that sort of digression for now. But one reason I wanted to talk about this one is Troy, you did miss you missed this E and the F, and I think you missed it just because it was up here at the top of the page, and it's a bit mean for them to have put them in up here. But there were these E and F over here as well, so I'm going to go briefly over those guys. Calculate the slope of the graph. What does the slope represent? Well, for E then, like I just did, the slope is 1.2. But we know that slope, right, is equal to rise over run, right, which is delta y over delta x, which in this case, we can easily say is, say from our very first point that we had, sort of 2.4 over 2, because if we look back at at the numbers that we have for a car crossing the bridge, we see 2.4 and 2 from 0, 0 over there like that, right? And I can do that out. equals y2 minus y1 over x2 minus x1, just to do it out totally, sort of pedantically, totally accurately. And that becomes 1.2, right? And that's 1.2 kilometers per minute. So they're going at a reasonable clip. 1.2 kilometers per minute is what? 72 kilometers an hour. Right? Yes, that's right. So they go 1.2 km per m is their speed. Right? Or we could say velocity, I suppose. This is a physics course now, so we could say velocity, but velocity has the difference between speed and velocity, Troy, you will see shortly. Maybe not this course, but certainly the next one. Speed has no direction component, whereas velocity has a direction. Um, Not a massive difference for right now, but you'll see later on that there is a difference. So speed of the current in kilometers per hour. Oh, well, look at that. 1.2. We can do it, say this, right? 1.2 kilometers per minute times 60 minutes per hour is going to equal, right, 72 km per h, because the minutes are going to cancel with minutes. So that's just a way that you can think about doing that one with the unit canceling method, right? That one should be fairly intuitive, but just to show how something intuitive still works out to have the same algebra requirements, basically, as any other sort of math like that. Boy, oh boy. Okay, we're getting through it. We're getting through it. So we're at about an hour in, and now yeah, this is roughly on track to get to the answer when I intended to finish. So the next part that I'm going to do is a little bit again in return to sine law and cosine law. So Betty Ann, these are a few of the questions that I was correcting for your the activity you submitted today. So I was getting to that one this morning, but I haven't been able to. I mean, it's difficult to devote much time to the ones that you know come in right away. But anyway, I'm getting through it, and we'll be there shortly for finishing these guys. But I'm just going to go over a few of the questions. I'm going to do them. Let's see. This is math 2101A, and this is unit 3 review. Here we go. Okay, so now we have this one is already set up, right? So these ones are a little bit different than some of the ones that you've seen so far because it already has the sine law sort of established here for you. But that's not it's not any more difficult. One reason I wanted to show these specifically is because I think you were just missing the step that you were supposed to do in order to get this b, get sort of the b outside of the sine, right? So here now we're going to be trying to find b by itself. So I'm going to cross multiply here, right, and turn this into 45 sine 52 equals 65 sine b. And it's important to note that when we're doing math like this, the numbers that are inside the sign here are actually never going to change until we do an inverse sign, right? Because they're sort of locked in there. They're inside that sign. And because like sine 52 is actually a specific decimal, right? And sine b, well, we don't know what b is yet, but it's sort of locked in there inside the sign. We can't move numbers in or out sort of without using the inverse sine function to get to sort of unlock it, right? Now I want to get rid of this 65, so I'm going to do 45 sine 52 over 65 is going to equal sine b. Now what I'm going to do is I'm going to calculate a decimal value for these numbers over here on the left. So it's going to be sine 52, right, times 45. It's going to give me that. Then I'm going to divide that by 65. So that's going to get me 0.5455, I'll call that, equals sine b. Like I mentioned, right? We can't access this b in here until we use anti-sign or inverse sign to sort of unlock this box, right? So that's going to be sine -1 of 0.5455 equals, I mean, what we're really doing is sine -1 of sine b, like that, right? But the inverse sign and the sine are going to cancel because they're operations kind of just like anything else, right? So we end up with is inverse sine of this decimal, which we're going to do like so, right? We're going to go second function sine over here to get that. Then I'm going to do this to put in this field, like I said before, just puts in the answer from the previous one. So it saves me rounding. Then it goes 33.06. So I'm going to call that about 33.1 equals B. Now again, as you noticed, as I was going down through, I wasn't concerned about sig figs for this one because this isn't a physics question. Although I guess to be fair, I should have been rounding to two places all along because it stands to reason that these angles, this 52, is definitely a measured quantity, right? But we don't, that's not something we had to concern ourselves with in this course. Let's do D here as well. So there's D. D is 85 over sine 80 equals 49 over sine C. So again, the same sort of deal, right? We can move sine C around just like any other number. We just can't mess with the C until we get rid of the sign. Okay, so now I can just go ahead and do my cross multiply. And this is going to be 85 sine C equals 49 sine 80, right? Because like I like to write out, A over B equals X over Y becomes AY equals BX, right? That's just sort of how cross multiplying works. So now that we have this, right? So we need to get this sine C by itself because we're trying to unlock that guy. So now I'm going to call this sine C is equal to 49 sine 80 over 85. Going to go ahead and work that one out. 49 sine 80 divided by 85. 0.5677. So then C is equal to inverse sine of 0.5677, or C is equal to, right? So the inverse sine of that answer, 34.6. 34.6 degrees, right? And it is always degrees because we can only take sine of degrees. Right? Let's see. There were a few other ones off this activity that I wanted to get to. So let me zoom out. Let me scroll on down here. Wanted to mention this one. I have to zoom out a touch. Right, here we go. So this is question 2C down here. Okay. So that way, that way, that way, then N O M 21.5, 21.5, 45 degrees, and an unknown side. Okay? So, Betty Ann, when you did this one, you set it up all correctly. I guess the error there might have been just, I think it was just plugging stuff into your calculator, maybe, because the working that you had written down was all completely correct, right? Because we know that C squared equals A squared plus B squared minus 4AB cos C. I think this is the one you had it correct, or was this the one where you left? There was one where it was all correct. I can't remember if it was this one actually or a different one. Sorry. Yeah, a lot going on at once. But either way, here now, we can go through and we can figure out what C is, but I've called this one C basically. It doesn't really matter. But that's the one that's by itself, right? So m squared is going to equal 21.5 squared plus 21.5 squared minus 4 21.5 21.5. I could have put squared there again, huh? And then cosine of 45, right? So then m squared is going to equal 21.5 squared. I'm just going to times that by 2 to save myself a little bit of work. 924.5 minus 4 times 21.5 squared, right? Times cosine of 45. But I put squared because there was 2 of them, right? Hold the phone. What did I just do wrong? Oh, it's geez, what am I doing? 2ab. 2ab cos c. No, excuse me. Excuse me. Sometimes, boy. Okay, so first two you did requires unknown side and angle, so you just found the angle, right? Um, do you mean, these two ones up here? Oh, those were the ones that we were just sort of given the whole thing from the start. Uh, you just found the angle. Yes, so these ones are finding angles. That's right. Yeah, because over here we know that this one and this one have to be angles. Yes, right. So this is 2ab. I don't know why I was putting in 4. I had the quadratic equation on my mind, obviously. So 21.5 squared times 2 times cos 45. There we go. That's the way. That's the way the cookie crumbles. That's how we do it. Actually, that's not what that saying means, is it? Doesn't really matter. So 924.5, subtract that answer, is going to be 270 point, it's about 270.78, right? But that's m squared, of course, right? So now we have to get m is going to be the square root of 270.78. So the square root of my answer for the last question is going to be m is equal to about 16.46. I guess that's in meters, right? No, inches. Inches. Okay. Yeah. These ones up here, Betty Ann, these first two. Um, yeah, I think when you cross multiplied, you ended up changing the value that was inside the sign, like here and here. So I just wanted to show that those ones we can't actually interact with at all until we use the inverse sign to kind of like unlock that sign function that's there around it. Some of the other ones, I think they were just sort of easy mistakes to make while going through, because everyone makes some mistakes while going through a math activity. Like, I mean, I just had a 4 put in there, right? If I'd have gone through, that would have made it wrong. But I knew it couldn't be that because I would have ended up with a negative value to take the square root of, and you can't take the square root of a negative, so at least not without going into it to imaginary numbers, which you will do eventually, but not right now. And you wouldn't see it in geometry because trying to represent, the square root of -1 in a geometrical sense. Well, I guess we kind of do. We kind of do it. We kind of do it on like an extra coordinate plane. But never you mind. just let teacher ramble for a minute about that, and then just sort of you know forget what I talked about. Now there are two questions here. I think. Um, Yeah, I want to do three questions next, and it's not necessarily because you did these ones wrong. Actually, some of these the answer key is wrong for, and I had to do a new answer key. So yeah, whoever made the answer key put a note alongside it saying fix this, and then didn't fix it. So here I go fixing it, I guess. Um, so this is math 2101A Unit 3 review. So question 4. Two ships left port at the same time. One ship sailed 90 kilometers, the other ship sailed 150 kilometers. If the angle between the ships at the time of departure was 70 degrees, how far apart are the ships now? Okay, that's a good question. So one ship sailed 90, one ship sailed more than 90, and then the angle between it is 70. 70 degrees, 90 km, 150 km, and then we've got to figure out sort of this unknown side over here then. There we go, that one there. So that's going to be x, right? Some very, very detailed boats I have here, right? They were rather simple sailboats we were using. How far apart are the ships now? Well, we see that we have two sides at an angle, and we need to find the other side. So that means we have to use cosine law, right? Right, so x squared, the one that we don't know, is going to be 90 squared plus 150 squared minus 2, 90, 150 cosine of 70. Right? X squared is going to be right, that's right, isn't it? Yep. So I'm just sort of going through and getting the answer for this one, right? And you can see as I'm working through, it's going to be 21,365 about that. Point, I'll call it point 46. So then x is going to be the root of that, which is going to be the root of that answer, which is going to be 146 about 146.2. All right, so they are about 146.2 kilometers apart for question 4. Okay, that sounds right. So I wanted to do, yes, 6 and 7 as well. So determine the perimeter of a concrete patio in the shape of a parallelogram. Ah, yes. So Betty Ann, I don't actually have yours corrected for this so I don't know if you did this one correctly or not. But the reason I'm going to do these next two on stream is because, like I said, they changed between doing the answer key and I guess posting it online or whatever. They changed parts of these questions, so I don't have a key for them. So I'm going to go through and do it out, and then we'll see together if it comes out correctly to what you did or not. I need to redo the whole unit. No, I wouldn't. I wouldn't say that. I think you're. I mean, from what I've seen, you're doing really well, except for the like there was a few small mistakes here and there, like with the cross multiplying in the first question that I did here today. But other than that, I mean, I think that there was a pretty good handle on a lot of these. Okay, so this is 79. This is 45. This is 13 meters. And this is 17 meters. And what are we to find out? Determine the perimeter of a concrete patio in the shape of a parallelogram. Oh, okay. Well, that's fairly good, right? Because now we can go ahead and what can we start filling in? And the stuff I fill in, I'm going to do in a different color. I'm going to do in red, so we see that it wasn't what we were given from the start. We know it's a parallelogram, right? We're told that. So if it's a parallelogram, we know this side is parallel with this side is parallel with this side. That means we can use our alternate interior, right? We can say that this is 45 degrees and this is 79 degrees over here like that. We can also get the other unknown angles as well, right? Because, of course, 180 minus 79 minus 45 is going to equal what? Not even going to do that in my head now. Minus 70. I should be able to, though, because 180 minus 79 is 101. 101 minus 45 is going to be 56. 56 is correct. So this angle here is 56 degrees, right? Which means this angle over here is 56 degrees as well. So, and we know that this is going to be 17 meters, because if it's a parallelogram, we know that this side and this side are equal. So now all we've got to do is figure out one of these two missing sides, and then we're sorted, right? So I'm going to go ahead and, let's see. I'm going to call this side X over here, right? So then we know from our previous ones, right, that, actually, no, we can go ahead and we can use this one based on sine law, can't we? We don't even need to use cosine law here, because A over sine A is equal to B over sine B, of course, like so, right? So now I can use either of these pairs, because I've got 13 and 56, that's a pair. I've got 79 and 17, that's a pair as well, right? And then I've got the 45 and the X that I don't know, that's a pair, right? So I'm going to go ahead and I'm going to start with the pair that we were given from the start, the 79 and the 17. So that's going to be 17 over sine 79. That's going to be the same as our unknown X over sine of 45. Now, so now this becomes very similar to those previous ones, the ones that we saw at the beginning of this sheet, right, of this activity. So now I'm going to multiply across, and I'm going to get 17 sine 45 over sine 79 equals X. And now instead of going through and doing out a whole crap load of decimals, I'm going to let my calculator do the heavy lifting. 17 sine 45 is that, divided by sine 79 is that. So that's going to be 12 I'll call that 12.25 equals X, like so. Right? So now I know that this one is going to be 12.25, which means this is going to be 12.25. So perimeter is going to equal 2 times 17 plus 12.25, because it's 2 times those two guys added together, which is going to be 2 times 29.25, right? Which is going to be 58.5 meters. There we go. So the perimeter for this shape is 58.5 meters. So like I said at the start, Betty Ann, I don't actually know if you got that one right or wrong yet, but I will find out after the stream is over. So I didn't have a key for it, and I figured, hey, instead of doing it out myself during my correcting time, how about I do it live in my math man time, right? That's when I put on my math man costume. Right? There we go. That's my attempt at a at a Adam West Batman style sound effect. Okay, solve the triangle if A equals M equals 6M, B equals 7M, and angle B is 65. Draw a diagram. Okie dokie. Let's go ahead and draw this diagram. This will be the last one that I'll do for today, unless 58.12. Okay, sure, that sounds about right. Yeah, that might have been to do with some rounding over here, because you notice when I did this part, what I did was I let the calculator do all of it. So because I left the signs in here and didn't round them myself, it actually used like 10 decimal places or whatever, right? So if you took it and took this value and wrote it out yourself and say used 1 or 2 decimal places, that could easily account for the difference of what, 0.38 meters over the course of the whole shape, right? So that sounds totally fine to me. So this is a triangle ABC. if A is 6 meters, okay, so this is going to be side A, so this is going to be 6 meters here. Side B is the side opposite angle B, so that's going to be 7 meters. And then angle B, which is this one here, is going to be 65 degrees. Draw a diagram. So there's my diagram, right? So now all I've got to do is, hey, look, I can use sine law, right? So I can use sine law actually to get angle A, because we know A over sine A is equal to B over sine B, like so on, right? So now, side A is 6, sine A is unknown, B is side B is 7, and then angle B is 65. So now I have that, right? So now I can go ahead and cross multiply. I do a full cross multiplying here, and I'll get 6 sine 65 equals 7 sine A. So I'm going to be dividing by 7. 6 sine 65 over 7 equals sine A. Well, I hope that I'm not getting like a shrill whistle when I do an S on my microphone, because boy, there's a lot of S sounds in this this unit. All these signs. So sine of 65. 6 sine 65. Oh, salacious. 6 sine 65. Divide by 7 is going to be that. So we're going to get 0.7768 equals sine A. This is getting foolish now. Okay, so now I'm going to do A is going to equal, I'm going to do the inverse sine of that amount. So I'm just going to write that out over here. Sine -1 of 0.7768. So then A is going to equal inverse sine of the answer of the previous one, about 51 degrees, I'll call that. 51 degrees. Okay, so I'm going to keep using red to show the ones that I filled in afterwards. So that's 51 degrees. Now to get C over here, of course, I can do 180 minus 65 and minus 51, right? Which is going to be 115 minus 51, which is, I'm not even going to do that. 180 minus 65 minus 51, 64. Right, so I know now that angle C is 64 degrees. So now that asks us to find. It said solve the triangle, right? So you don't see that terminology used all that often for whatever reason in this course. Solve the triangle. But what we mean by solve the triangle is just like find all the unknown bits, right? So I'm going to go ahead now and I'm going to find C, because I know now that say 7 over sine 65, which is still the other one, is going to be side C over sine of 64. And we see that the angles are almost equal. They're almost equal angles, which means the sides are going to be almost equal as well. So we're going to get an answer very close to 7 here. But now we have 7 sine 64 over sine 65 equals C. And now, just like before, I'm going to let my calculator do a lot of the number crunching for me instead of writing it all out. I'm going to do that over here. So 7 sine 64 is that, divided by sine of 65 gives me 6.94. There we have it. So that is the solved triangle there. Hi, Wagner3. Hey, how you doing? Thanks for dropping by. But yeah, Betty Ann, I think that should cover your all the questions from that activity pretty well. So I will now be able to go back and check and see if you have indeed done questions 6 and 7 correctly, because this will be my new answer key for those. I hope that answers any questions that you might have had about that topic. Yeah, if you're working over the weekend or on Monday or whatever, and you have any more things to ask me about those, you can just fire off an email, and I will get to those on the next stream. Right, but we are of course about winding down for the day. Yeah. Yeah, Wagner. You're welcome. Very welcome to come and hang out. Though I'm a currently working teacher because us teachers working via distance are um, have a fair bit to get done during social distancing. So I will be ending the stream here shortly. Though if you have any questions for me about any math or the physics or the stuff that I've been doing, please you can drop that in chat, and I will definitely get to that before we're done here today. But either way, I'm going to bounce back over here to my intro screen just for a quick second here, right? So we covered significant figures, intro to distance, time graphs, rearranging common physics formulae. Got those ones done. Um, yeah, my nice little diatribe about the order of all the different orders of playing cards, right? That was fun. That was fun. I like that one. Cross multiplying sine laws, sine and cosine laws, and angle properties. We got there. All right, so I'm going to leave you again with one last look at the classroom that I taught in for a year in one of my positions in England. Right? Yeah, I don't know. Not really a longing look per se. I mean, are you ever looking longingly at your previous work site? I don't know exactly, right? But it is something to review. You'll see over there above the books actually. That was what I called the marvelous list. That was quite fun. That was this effect to try to get students to I don't know, to behave, I guess, to be marvelous, right? I had a math star. That was quite cool, right? This little like medal that you would put around your neck to be a math star. Well, that one didn't get given out that often. We did have these little cards, these little like credit card sized cards for like good citizenship awards. And we're giving those out to students for like various discussions that we had that were quite engaging, right? That was some of the various little things that we tried to do to increase student engagement in the school, like so. Actually, plants can photosynthesize with fluorescent light. Um, yeah, I'm not so much a biologist, but I believe so. Yeah, I think there are specific kinds of light. I think that plants need to photosynthesize, right? Like it's ultraviolet light. I believe you need a special sort of like UV lamp. I think for plants to photosynthesize like inside, basically. I don't think just any random fluorescent tube. I believe those don't work. I don't think it has to be an ultraviolet light specifically, right? I'm not super well versed in the interior growing world, although though I am interested in the. I might set up a greenhouse actually at the cabin. There's something I haven't talked about in like 3 or 4 days. The cabin. Yeah, I do. I would like to set up a greenhouse out there, but we wouldn't need UV lights or anything in a greenhouse. But I am pretty certain, yes. But you should be able to find lots of resources online about that. Maybe your hydroponic setup, got to stick it in like a closet with a false front, so you can open it up, and in behind you got your herbs growing, right? My plant's gonna die. Oh no. You know. Anyway, thanks for dropping by. You're more than welcome to come by and ask any questions you like. Um, Monday when I'm back, start at 1 p.m. Newfoundland time, which is 11:30 Eastern. Usually go for an hour and a half, maybe 2 hours if I'm pushing it. But I do have end of the week paperwork to get to at my job, and I would like to be done before 5. So I'm gonna skip on out and do that there now. But yeah, thanks for joining me for today. Hope it was interesting, engaging, compelling, and captivating, or at very least one of those. Right? Stay safe, and yeah, hope to see you again on Monday.